Hello everyone, ladies and gentlemen. My name is Alireza Abdollahpouri and I am an associate professor of computer engineering at the University of Kurdistan. In the next 15 minutes, I'm going to share our recent research experience on link prediction and multilayer networks. I'm presenting this paper on behalf of my master's student, Mrs. Samira Rafiei. The title of presentation is a new interlayer similarity metric for link prediction in multilayer networks. So to begin with, let's take a glance at the outline. As you can see, I have divided the presentation into 5 parts. At first, a brief introduction is given and trying to motivate you about the importance of the problem. At the second part, some background information is given. And then the proposed method is introduced, and after that the results are evaluated on both real-world and synthetic networks, and finally I will conclude the presentation. So let's turn to first part, which is introduction. As you may know, many natural, biological, and social systems can be modeled as networks. For example, Facebook network is a graph of friendship between people, or PPI network is a graph of interaction between proteins inside a human cell. Some of the networks are not static. I mean, they have a dynamic structure. For example, in collaboration networks, sometimes a new author can appear, or old authors may disappear, or new collaboration can be initiated, or maybe previous collaboration stopped. The problem of link definition is that we have a snapshot of the network at time t, and we want to know whether it is possible to predict some new links in time t+1 or not. So we want to know whether it can predict some new interaction between members in the future or not. This prediction is based on some sort of proximity or similarity between nodes in the network. The link prediction problem can be viewed from 2 different perspectives. The first one is estimation of likelihood of the existence of a link between any 2 nodes. This estimation is based on the attributes of nodes and observed links. And the second perspective is identification of missing links, or link completion. Link prediction has many applications, such as proposing friends in Facebook, or recommending matches in Tinder network, or proposing items to purchase for customers in Amazon network. Some of the networks can be modeled as multi-layer structure, or multi-layer network. We can call them multiplex network. For example, assume we have 5 cities, C1 to C5, which are connected by different transportation systems, such as rail, road, and air. Each of these transportation systems can be assumed as a layer. In this network, we have 3 layers. Layer 1 is rail, layer 2 is road, and layer 3 is air. Accordingly, we have 2 different types of links, which are interlayer links, the link between 2 layers, and intralayer links, which are the links between 2 nodes in a single layer. The question is whether it is possible to predict links in one layer, taking into account the structural information of other layers or not. For example, if we know the friends of someone in Facebook, is it possible to recommend new friends to him or her in Instagram or not? So let's turn to background section. In recent years, a lot of research efforts have been devoted in this regard for predicting links in single-layer networks. And therefore, a couple of methods have been proposed. which can be divided into two main categories. Some of the methods are based on local information, such as common neighbor, Jaccard coefficient, atomic radar, professional attachment, and so on. And some are based on global information, such as cache, PageRank, and routed PageRank. We have also proposed a new intra-layer similarity metric called common neighbor degree penalization, or in brief CNDP. In our method, we have taken the clustering coefficient of nodes into account, and there are also several methods for link prediction in multi-layer networks for predicting interlayer links, such as degree-degree correlation, method based on bitwinness, and the method based on average similarity of neighbors. Okay, so let's turn to our proposed method. At first, we need a definition. Assume we have a multi-layer network G, which is composed of n different layers, L1 to Ln. Each Li is a graph of a set of V nodes and EI edges. So as you can see, the set of nodes is fixed for all layers, but each layer has its own specific set of edges. At first, we have to calculate the distance of node degree in two layers. The distance of node degree of Di in layers Lm and Lk is calculated according to this equation. You can subtract the degree of layer I in Lm and the degree of layer I in Lk, and then we can calculate similarity of nodes, node degree in two layers Lm and Lk, and then similarity of two nodes I and J. And based on these equations, we can define our new proposed interlayer similarity matrix between two nodes I and J. Here you can see the pseudocode of our proposed algorithm. It's not so complicated. It's composed of two parts. The first one is finding the distance and similarity of nodes in different layers, and the second part we calculate and combine inter and intra-layer similarity metrics. So interlayer similarity metrics is according to what we have discussed in previous slide, and intra-layer similarity is according to common neighbor degree penalization, which we have proposed in our last paper. So let's go to evaluate the results. To evaluate our proposed algorithm, we used 4 real-world networks and 1 synthetic network. The real-world networks are Twitter, Facebook, Twitter, Instagram, online and offline relationships, and air transportation network in Europe. The first one is 2-layer networks, second one and also 2-layer, and the third one is 5-layer network, and the fourth network is a 10-layer composed of airlines, different airlines in Europe. And our Barabasi-Albert synthetic networks is generated according to Barabasi-Albert method with 5 initial nodes and final 1,000 nodes. The evaluation matrix is AUC, or area under the ROC curve. AUC is a well-known evaluation matrix for checking the performance of classifiers and predictors in machine learning. It's based on the area under the ROC curve. ROC curve is plotted with the true positive rate against false positive rate. And so in this figure, the straight line is a complete random predictor, and the pink curve is a good predictor, and the yellow curve is an excellent predictor. The highest value of AUC is 1, And the AUC value of 0.5 means that the classifier is not able to distinguish between positive and negative class points. It performs completely random. In this table, you can see the AUC values for Barabasi-Albert artificial network for different values of p-copy. P-copy is the probability of copying a link from the first layer to the second layer. So in Barabasi-Albert synthetic network, we have two-layer networks. Our method is DS, or distance similarity, which is compared with 3 other methods. As you can see, for all values of p-copy, our method performs higher values for AUC. Similarly, for real-world networks, as you can see in this table, our proposed method performs better and provides higher values of AUC in comparison with a recent method. This is called LPIS. Okay, to sum up, we proposed a new interlayer similarity metric for predicting links in multilayer networks, and this proposed metric is combined with our previously proposed strong interlayer similarity metric CNDP to improve the performance of link prediction. And finally, we evaluated our proposed method on both real-world and synthetic networks, and they showed that our method outperforms similar methods in terms of AUC. So thank you very much. Thanks for your attention. I think from this moment we have 5 minutes for discussion. I will be very interested to hear your comments and questions. Thanks again.